whether what we have on Earth is representative of what's currently in space is a big question. We have a very biased collection.
You're listening to The Cosmic Cast.
Good morning, afternoon or evening, and welcome to another episode of The Cosmic Cast, brought to you by the Earth and Solar System team at the University of Manchester. I'm your co-host Marissa Lowe, joined by John Pernay-Fisher.
Hello.
And Elliot Carter.
Hello.
Our guest this week, joining us from the Natural History Museum, is Helena Bates.
Hello.
Hello, Helena. Thank you very much for joining us. How are you doing
Thanks
today?
for having me. I'm doing okay. It's raining, so it's a bit miserable, but yeah, doing okay.
Good. So you study meteorites, I believe, at the Natural History Museum. So in particular, you look at carbonaceous chondrites. So would you mind explaining to us what those are and why you're studying them?
Of course. So carbonaceous chondrites, so meteorites in general, come from all sorts of places in the solar system. So you have Martian meteorites, you have lunar meteorites, but most meteorites come from asteroids. And asteroids are rocky bodies, the building blocks of planets, things like that. But asteroids themselves come in kind of loads of different flavors. So you get asteroids which were really large when they formed, and when they're large enough and they have heating on their interior, they differentiate into a core and a mantle and a crust. And we have meteorites from those. Some examples are the HED meteorites, and they come from a very large asteroid called Vesta. But then you have asteroids which were kind of large-ish, but not quite large enough to have melting on the interior. They were just heated, and those produce meteorites, but they're kind of processed a bit. They've been metamorphosed a bit, but not that much. And then you have asteroids which kind of never really grew large enough to have anything happen to them. So these kind of just are random accretions of the stuff that was existing before planets. And those are the primitive asteroids, and they produce primitive meteorites. And carbonaceous chondrites are a group of primitive meteorites that come from these very, very primitive asteroids. So they're super duper old. They're essentially snapshots of the solar system when it was just forming. And the carbonaceous chondrites contain, as probably the name suggests, a high-ish abundance of carbon. So that's what's interesting. They're super duper old, super duper primitive, and they have some carbon in them, which is kind of exciting. Yeah.
Amazing. That was an amazing overview there. So what samples in particular are you looking at?
So unfortunately, meteoriticists really like classifying things. So I say, we've got these different types of meteorites and these different types of asteroids, but then carbonaceous chondrites themselves are also split into a bunch of different types based on a variety of things like their petrology, like their isotopic compositions, things like that. But the ones I look at are called the CM and the CI carbonaceous chondrites. And so those meteorites are named for like a type specimen. So the CM chondrites are named for the type specimen MIG-A. So all CM chondrites look like MIG-A, I'm not sure. And then CIs is the type specimen is a Vuna. So all CIs look a little bit like a Vuna. And the thing that's really special about the CMs and the CIs is, even though they're super duper primitive and super duper old, they look as though at some point in their history they were exposed to water. So they're made up essentially of clays, of phyllosilicates. And so looking at them gives us some insight into the role of water at this really beginning stage of solar system evolution. So they're the specific ones I look at. Yeah.
So this is probably quite a big question. You were mentioning like there's carbon in these chondrites and also water. Mm-hmm. Where does all of that come from? How is that ending up in our meteorites?
In the meteorites, well, we think that they're just almost direct condensates from the solar nebula, or water especially. It's probably a direct condensate from the solar nebula. So you might have heard of the snow line, which is the point of the solar system beyond which water ice, like in the early solar system, I'm going to keep referring to the early solar system, all this nonsense, but temperatures were really, really hot, close to the sun, but cool further away. And so the snow line is the point at which temperatures were cool enough for water ice to condense and be part of the accreting material. So we think that the CM and CI carbonaceous chondrites came from asteroids which formed outside of the snow line, so they could accrete water And then that water would melt through radioactive decay of aluminium-26, so like radioactive elements, and interact with the host rock and change it into the phyllosilicates. And actually, in some cases, we have an ammonia snowline as well. That's how you get the carbon. So it accretes. So the meteorite accretes ammonia ice, and then that can also melt and interact and create carbon-rich rocks, basically, or carbon-rich material.
Yeah.
So, yeah.
Yeah.
It's not. It's exciting. Nobody really knows, really.
Yeah, but I feel like in lots of planetary science questions, it's always, well, where is this coming from? And where is this coming from? And you go back and back and back, and you're probably looking at the stuff that is the first origin. Where did it come from? In this very long story.
Yeah, like the Big Bang. So yeah, it's the easy answer to everything. So
Yeah.
But I guess also, I suppose, I guess some of these water-rich chondrites, then is that what people think where the water on Earth came from as well?
yeah, so there's this theory that the Earth accreted too close to the sun to have water ice as part of its accreted material. It accreted inside the snowline. So water must have been delivered from an extraterrestrial source. So you're right, like these water-rich asteroids are currently the leading theory as to where it's come from. There's actually been a recent study that suggested that the material Earth was accreting from, which is actually represented by a different group of meteorites, may have a bit of water in it as well. So it's probably a multitude of sources that have delivered this water. So, but these asteroids are pretty good contenders, really.
Yeah. So I guess it's probably not too relevant for most of our audience, but I guess the CI chondrites are particularly interesting because I guess that's what most geochemists use to normalize geochemical plots do, isn't it? So I guess it's, in that respect, it's an important group of meteorites.
Yeah, it's the one sort of meteorite type that most geologists will have heard of because everything is normalized to CIs. And that's because if you disregard hydrogen and helium, CI's composition matches that of the sun. And so and because the sun is 99% of all of the mass in the solar system, we take that as the mass, the composition of the solar system, basically. So everything is normalized to CIs because that's what we think basically the solar system is made of.
Yeah. So as the years gone on, then have people found then that the compositions of these groups have been quite sort of homogeneous? People haven't found that actually CIs can be quite heterogeneous in their compositions, or?
Oh, people have found so much heterogeneity in meteorites. It's an absolute nightmare. They vary a lot. CIs and CMs especially because they're essentially breccias. They're like regolith breccias because they are just like rocks that stuck together. So they vary a huge amount. And I always find that if you end up looking at a meteorite, a carbonaceous chondrite in any detail, it will be different from what you thought it was, and it will be its own unique thing. So, I mean, we have found the CIs, there aren't very many CIs, so that's why it's quite useful to have them. There's only about 5 official CI chondrites, so that's kind of okay. They're big, we've got quite a lot of them.
They're still fine to normalize too.
They're still fine to normalize too, but a lot of CIs that have been found, these are all falls. So meteorites are, you probably know this, classified into ones that are seen, observed to fall, and ones that are just like found on the ground. And CIs, because they're these water rich or they're made of clays, they're really susceptible to terrestrial contamination. So they're best when somebody sees it fall and then you can be like, oh, let's go get it before anything happens to it. And there are only 5 of them. Any that have been found later have been found to be something different, basically.
So if I was to hand you a chunk of one of these 5 CI meteorites, what are you going to do with it? To find something out about where it came from?
Well, I mean, I guess geologists would give you a different answer, I suppose. What I would do is, and this isn't what I did in my PhD at all, I would probably do a micro CT scan. I don't want to destroy it at all because it's very, very precious. So I would try and focus initially on the non-destructive things, do some micro CT, see what the distribution of things like metal are, because obviously these meteorites, because they haven't been differentiated, often have quite a lot of metal in them. And that's really interesting. And then you might maybe make some sections, do some analysis on the sections, get some EDS maps, things like that. But that's not what I did. So
I guess that leads on very nicely then. So what did you do during your PhD then?
So I was interested in how these meteorites we have on Earth are similar or not similar to the asteroids that are still in space.
Okay.
Yeah, so I basically looked at, my primary technique was a technique called infrared spectroscopy. So I would collect the spectra of meteorites and compare it to the infrared spectra of asteroids that are still in space. But with the meteorites, what I would do is like classify, or not classify, so they'd already been classified, characterize them, so work out what's in them, come up with a kind of story for how they formed, and then like get the spectra, and I could be like, oh, it looks like this because it's got that in it. And then when I look at the asteroid, I'm like, oh, it looks like that, maybe it's got that in it. And it sounds quite like sort of logical, but asteroid data is rubbish, so it was harder than it sounds. So yeah, that's basically my PhD in a nutshell.
I guess no, that's really cool though, and that's something that we've never really touched upon, isn't it? I suppose then. So I guess you're sort of implying then, I guess, that we don't really have a firm handle on where within the meteorite belt and all that kind of stuff, all the different groups of asteroids come from. Then would that be fair to say?
Oh, completely. There have been so many. So asteroids also have their own set of classifications, right? And so many people have been trying to match asteroid types to meteorite types, and they said, oh, the C-type asteroids match the CM chondrites. And in fact, that's why they're called C-type asteroids. But then there's loads of things you can't explain. And the other big thing is that obviously the asteroid that created the meteorites probably doesn't exist anymore, because it's been broken up and has rained on the ground as meteorites. So whether what we have on Earth is representative of what's currently in space is a big question. We have a very biased collection. So who knows, really? It's not easy.
And I guess, as you were suggesting just now as well, I suppose, as you said, the spectral data that you've got for the asteroids is nowhere near, because I guess you typically just have like certain wavelength bands, don't you? So aren't you trying to fit spectra to only a couple of different points, whereas you've got these really nice high resolution data from then the actual meteorites?
Exactly, that's exactly the case. I mean, we have decent asteroid data in the visible and near infrared wavelength ranges. So this is 0.3 to about 2 microns, which is a very small area. And basically the only features you have in that zone are a whopping great silicate feature at 1 micron and a whopping great silicate feature at 2 microns, and that's it. If you're looking at something which is clay-like, or maybe it's got lots of magnetite or metal in it, you have just a straight line. And so you're trying to match slopes, basically. There's a really interesting, but then it's also affected by absolutely everything else as well, like how you're viewing it, and whether space weathering is a massive issue and that kind of thing. So it's constantly, these links between meteorites and asteroids are constantly being revisited and like kind of reanalyzed and things like that. So
that's cool. So were you using mostly published spectral data, or did you have a chance to collect some of your own observations?
So unfortunately, I was not using published asteroid. I was using published asteroid data. There are only a few telescopes on the ground that can like collect. Because I was looking at, so I mentioned the visible and near infrared wavelengths. I was actually looking at the visible and mid-infrared wavelength ranges. So this goes up to about 50 microns, from about 2 microns to 50 microns. Because there are unlike the slopes that you get in the visible, there are loads and loads of features in that wavelength range. And there aren't very many telescopes that can collect asteroid data in that region. And the other thing is ground-based telescopes are also heavily affected by the atmosphere in those wavelength ranges. So there's the infrared telescope facility, NASA infrared telescope facility in Hawaii, which unfortunately I never got to go to. And then there's then there are a few space-based telescopes. So Spitzer was a big one, but Spitzer was unfortunately retired. I mean, it went on for a lot longer than it was meant to. I think it was retired in 2019. But yeah, most of the data had been collected previously. There's not much out there. in those
Yeah.
wavelength ranges. So
Yeah, I hadn't realised there were so few telescopes then that could make those kind of measurements. That's quite surprising, really.
I mean, I mean, to go up to like the longer wavelength ranges to collect in the mid-infrared, there's really very little out there. But actually, I mean, you'll find that there aren't, just in general, aren't very many telescopes that will collect it at all. So most of them, like the NASA one is the big one, basically. And if you look, you're like, oh, there's so much spectral data available. It's pretty much all collected by them. So,
Yeah.
So which are the main asteroids that you were comparing your meteorite samples to?
So I was primarily looking at, obviously, asteroids, which have got data, and those are limited to the ones that are of interest, scientific interest for other reasons. And obviously the big two that are of interest currently are the targets of 2 sample return missions. So we have NASA's OSIRIS-REx, which went to Bennu, asteroid Bennu, and we have JAXA's HIBIS-2, which went to Ryugu. And both of them have obviously had the telescopes trained on them from the ground in preparation for those missions. So there's quite a lot of data out there. But so a lot of my work was motivated by trying to compare the data to those 2 asteroids. But I also was lucky enough to have a look at, or to get a hold of some data for some Jupiter Trojan asteroids, which were pretty cool, and just some main belt other bits and bobs, basically whatever I could get my hands on, really. So yeah.
Yeah,
From
of course,
all your
because
work, were you able to suggest any links between asteroids, or was it more like a roadmap for like, here's how you might link these things?
So I didn't come up with any like new links, but one of the things that I was able to do was come up with some parameters which I could then apply to the asteroids to give an idea of their surface composition. So for example, I found that there was a relationship between the area of a particular feature, and its magnetite abundance, for example. And so I could then use the area of the asteroid feature to say, okay, well, that has 5% magnetite, that has 3% magnetite. So it wasn't particularly revolutionary, I think, what I discovered, but it all kind of adds up together to build a picture. So
Yeah. So I guess going to the other end then, so I suppose it's difficult getting good spectral data for the observations, but then on the other end, is it difficult getting good ground measurements on the actual meteorite samples, considering how heterogeneous they can be? Have you had to work with like very large sample masses to get good representative
oh my goodness.
measurements?
Yeah, you've touched on a big issue here. Like this was a nightmare. Yeah, meteorites. So the whole aim, or the whole kind of, I guess, the motivation of the project, apart from trying to work out what was going on with Bennu and Ryugu, was that a lot of people, when doing comparisons, like looking at meteorites, will say, just collect a spectrum of a meteorite and be like, well, that's MiG-A meteorite, that's a CM meteorite. It looks like that because, but they don't know what's in the sample before they collect the spectrum, and you're like, what are you doing? Essentially I used the same material throughout my entire project so that I could really definitively link spectral features to compositions, but which is something that people just don't do. They assume that meteorites are homogeneous. So yeah, I use the same material throughout because of that.
Yeah.
So.
How do you make the surface, or like, does the surface you're looking at matter? Like, is the surface of a meteorite the same as the surface of an asteroid?
Yeah, I think there are entire PhD projects devoted to this. So I ground my samples up into a powder, which means that my spectra will only be comparable to an asteroid surface which has a really fine-grained regolith, like the moon. So the moon has got a really nice fine-grained regolith, and so we thought when we were going to Bennu and Ryugu, they will also have a nice fine-grained regolith. So all of our preparation has been on powdered samples. Little did we know, we got there, no fine-grained regolith. So all of us are like, oh, that's good, isn't it? All of this data's been collected on powders, and turns out there's no powders on Bennu and Ryugu. So, yeah.
Why is that?
Well, that's a really interesting question. There are a number of theories as to why there is no regolith on these asteroids, because there are obviously processes going on that would create regolith. So you have thermal fracturing of boulders and all this kind of thing that should create regolith, but there is none there. oh, there's not much there. And so a couple of people have looked at potentially it like particle sorting. It's sinking down past the sort of surface layer of like chunkier boulders. There's also some asteroid activity been observed on Bennu. So this is when activity is what you use to describe what happens on comets. So when all of that material is lost, there is some evidence that Bennu has the occasional like burp, basically, where some material is like lost from the surface. Whether that's going to be enough to get rid of all of this like suggested regolith, I don't know. But it was very surprising, and no one really knows.
So at what point was Hayabusa 2 and OSIRIS-REx, all the news with that happening during your PhD then, and how has that affected your project?
Well, I mean, in a kind of quite like sad way, it's made my project quite sort of sexy for people. So I've been, you know, like a lot of people, my university, for example, because I was based at the museum, I also have a host university. I should probably shouldn't say this. I probably shouldn't say they took advantage of me, should I?
We can cut that out.
Yeah, just I feel bad saying that, but yeah, I mean, it's made it a sexy subject. So I have had the opportunity to go and do lots of like people have asked to come and have me talk about the missions and things like that, which has been an amazing opportunity for me, really amazing opportunity for me. And they haven't been taking advantage of me at all. But so Hayabusa 2 launched in 2014. So I started my PhD in 2016. So Hayabusa 2 launched in 2014. OSIRIS-REx launched in September 2016, so like a month before I started. And both of them arrived at there. So Hayabusa 2 arrived, I think, in August 2018. 2018, I think. And Bennu arrived in December 2018, I think. I think they both arrived within 6 months of each other. And so that was really exciting because at that point I was 2 years in, everybody was talking about it and everybody was like, the work you're doing is going to be really useful for this. And I was like, yay. So yeah, it's been nice because like Hayabusa 2, I was in Japan around the time that they did the sampling of the surface, which was really cool. I was there for a Hayabusa symposium thing, which was really cool. But it's made my work feel more important, which is a really important thing, I think, sometimes when you do a PhD and you're doing something so specific that often you sometimes don't really get that validation that what you're doing can be useful and stuff. But because these missions were going on, I got that validation from people, which was amazing, like really amazing. I'm so lucky. So, yeah.
Yeah, no, that's great. It's all these poor people that work on Venus, they're just hoping one day they'll be relevant.
I know, and then they had the phosphine paper, and then they were like, and then maybe not. I don't know. Venus is really exciting though. I think Venus is the next big thing. So I say that with no knowledge. Like I don't know what the next big thing is. So
Yeah.
I think Venus is cool.
Venus is
amazing.
Yeah. But anyway, I guess we're getting sidetracked.
When are they due back, the samples? They're not back already, are they?
So Hayabusa 2 arrived back on December 6th.
Yeah.
So one of my Viva examiners was involved with it, so we had to make sure my Viva was afterwards. It was all very exciting. But Bennu, OSIRIS-REx isn't back till 2023, 24. So it's done its sampling, but it's not going to be returning until.
Okay.
What? I don't know. This might be a stupid question. Why has it taken so long for one of them?
So Hayabusa 2 only took about 4 months to get back, and that's just because of the orbits of Ryugu being close to Earth at that point. OSIRIS-REx, and that's also why Hayabusa 2 took a really long time to get to Ryugu, whereas OSIRIS-REx didn't take as long. It's all to do with mutual orbits of things. But OSIRIS-REx, I think when it leaves Bennu, it's going to be quite far away from Earth, so we'll need to do a couple of like goes to get back.
Yeah. And how much have they collected?
Well, Hayabusa 2 was like, both of them have been really, touch wood, successful because Hayabusa 2 aimed to bring back 10 milligrams, right? 10 milligrams. No.
So little.
Yeah. Was it 10 milligrams? Was it that small? Was it really that small? What they were going to bring back? Very small amount, basically. But they brought back 5.5 grams, which was really nice.
Whoa.
Yeah. So for a terrestrial geologist, you're like, what? Like 5 grams? Like what? For us, we're like, my goodness, this is amazing.
That's the kind of amount I drop on the floor when I'm being careful.
Well, I do have some absolute horror stories dealing with meteorites and spilling them down myself. So it does happen. And then OSIRIS-REx, obviously we don't know because they haven't brought it back yet, but the sampling, they were aiming to bring back 2 kilos, so much, much more. And when they did the sampling, their sample head, the sample capsule container has got like these flaps, mylar flaps, where material was going to like flow in, and then the flaps were going to close. And after the sampling happened, they took a photo of the sample head thing, and they saw material escaping from the surface because there was so much in there that the mylar flaps had been wedged open. So they found they think they've collected over 2 kilos of material, I think. So they really quickly stored it in the return capsule, so it's all safe now. But yeah, that was a big concern.
I think I remember that on the news. Like, I think at one point they were talking about flying back with it open and hoping it didn't all fall out.
Well, I think it's basically that's kind of what they're doing, because these mylar flaps might just be open inside the sample return capsule. So
Is it just like driving off and you've accidentally left the boot open?
it's more like I suppose if you've got bags in your boot that are open, the boot's closed, but then you have to travel through Earth's atmosphere, so everything's going to go everywhere.
Nightmare. But yes, how on earth did you get to studying space rocks?
So I always really loved space. I don't think there was ever any time that I didn't want to study something to do with space. But I was awful at maths. And so I thought, I can't go and do physics, which is what I thought was the only route to go into studying space, because not only was I awful at maths, I just didn't like it. Didn't like maths at all. And so I remember like looking up things to study at university, because I was like, studying space is never going to be an option. And I found geology, and I remember going to an open day, and this guy giving a talk, and he was like, geology is the study of rocks, but not just rocks on Earth. And I was like, oh my goodness. And so I decided to study geology. I actually applied originally. When I started my undergrad, I was doing geology and geophysics, because that was a course my university offered. But then actually after my first year, turns out, as much as geology might have sounded great, I didn't really enjoy being out in the field, which is quite an important thing if you're a geologist. I also didn't really like looking down microscopes. Again, quite important when you're a geologist. I preferred the kind of, weirdly enough, because I didn't like maths at all at school, I preferred doing the maths and the programming side of things. So I ended up switching to straight geophysics, and did my undergrad and integrated masters in geophysics in the end. And then, so my undergrad was at Imperial, and so I was really near the Natural History Museum. And I remember emailing Sarah one day, being like, hey, can I come and visit? Because I love space. And I was so lucky that I emailed her like that week, because she just got news about like an internship. Like there's a you might have done them, a Paneth internship, which is a meteorite. This man called Mr. Paneth, I think, donated some money to basically fund undergraduate internships in planetary science. And I managed to do one of those with Ashley King, who was my supervisor in my second year. And then I kind of just never really let them go. I was like, can I apply for this? Can I do this? Can you help me? And they were like, oh, fine. So that's kind of how I ended up doing it.
And what's it like working at the Natural History Museum?
It's great. It's good. So I don't know if I'm currently the interim meteorite curator. Don't know how that happened, but now I'm technically, because Natasha is on maternity leave at the moment, so I am in charge of the meteorite collection. And if she sees this, I'm looking after it very, very well. Nothing is going wrong. I promise. But that's great fun, because obviously I was a kind of external person. I was externally funded when I was there doing my PhD. So you kind of do your own thing as an externally funded person. But then now that I'm more involved in the actual inner workings of the museum, I get to see all these like interesting discussions and all of the politics, and it's been good fun. I mean, I love working at the museum. It's great. You can be forgotten sometimes as a student, but it's great. So.
Yeah. Amazing. Yeah, it must be an amazing place to work. I somehow only managed to go for the first time like 2 years ago. I think when they had all their when they had the massive like moon exhibition there.
The moon balloon.
Yeah.
Technical term, moon balloon. Yeah, it's great. If you ever walk past the front and you look, I'm looking out over where basically the ice rink is normally. You see a blow up green alien in one of the windows on the ground floor. That is my office. So yeah, it's a great place to work. I mean, I think I'm super duper lucky, super lucky. So it's awesome.
Cool. Wonderful. Are there any other bits, John or Elliot, you wanted to?
Well, I think we just have one more question, really, and this is the regular question that we ask all our guests. So if you had to start over and planetary science was not the field you were going to go down, what else do you think you might have gotten into?
Oh my goodness. Well, I think, do you mean like if I was still doing like, okay, so I think probably, I would train to become a sommelier.
Yeah.
Yeah, so I love wine. I love wine, but I also find all of the stuff about wine fascinating, like the history, the geology of it.
Yeah.
And so one of the great things I've been able to do in lockdown is to study for my Wine Spirits and Education Training Awards. So I've been doing that, and I actually have an exam on the 20th. Let's hope I don't pass. Let's hope I pass. Oh my goodness. But I think, in another life, I could see myself opening a wine bar and going and traveling around Rioja in Spain and getting really nice red wine, travel around Bordeaux a bit.
Yeah.
Nice
That sounds amazing.
Yeah, that would be great.
What does the exam involve? Like,
just going to ask,
wines?
because it sounds like it should be quite a practical subject.
Yeah, so the stage that I'm at, it is just a multiple choice exam. The next stage, if I wanted to continue on, I would have to do a blind tasting. But I think, from what I understand, I mean, there's no wrong answers when you're blind tasting something. What they're interested in is if you do the kind of like appropriate methodology. So it's like, I guess it's a bit like science. Like if you taste it and you're like, well, I can taste blackberries, and you write down, pronounce primary flavors of blackberries. Like, even if it doesn't actually taste the blackberries to the person who's marking your exam, that's still a valid observation. So, yeah, but it does get more practical after the stage that I'm at now. So, but the training itself, there's lots of tasting, which is great. So that's been good fun. Nice thing to do over lockdown on a Monday afternoon. So
yeah, absolutely. That's amazing. That's so cool. I imagine sommelier jobs, there must be quite a lot of competition for those kind of positions.
Yeah, I think so. I think you have to probably have to get quite a lot of qualifications. So there's only about 200 masters of wine in the world, maybe 300 masters of wine in the world.
Wow.
So, but that's obviously, you don't have to be a master of wine to be a sommelier. In fact, I don't even think you need to have any qualifications to become a sommelier, but I think having these Wine Spirit and Education Trust Awards help. So who knows? I mean, academia is a difficult career choice.
Yeah.
So Who knows? In a year's time, come visit me in my wine bar.
Yes.
Do you think you'd ever get into? Sorry, Marissa.
As you said, the geology. Did you say the geology of the place can affect the wine? You can be a wine geologist. That's perfect.
I know.
Well, that is a thing, isn't it? I think there was in my undergrad there was in the geography department there was a professor of wine geology. They used to do a course for that.
I think there's a special issue of Elements. I think it's
Yeah.
Elements.
There was. I have that. Of elements. I mean, there are a lot of elements that I have binned, but that one I didn't. So, yeah, there's because like things to do with like the soil. The soil is really interesting because nobody really knows. You understand how certain soils can like help grapes ripen, but nobody really knows why certain soils give certain flavors to wine, for example. But you have things like whereabouts on a slope you plant makes a big difference. Why you have only some vines that can qualify for a certain status of wine is to do with where it grows and how it grows and your environment, which is basically geology and geography. So there's a lot of interesting stuff going on.
Yeah, right. So you've definitely got to come back, and we can talk. We have to talk more about the geology of wine. I think that'd be
yeah.
great.
I'll do a guided tasting where I can tell you about all of the geography and geology of where you're tasting the wines.
That'd be excellent.
Yeah, that'd be great. I'd love that.
Amazing. Well, thank you, Helena, for joining us today.
No worries.
And best of luck with your research over the coming months.
Thank you.
Yeah.
Well, thank you for having me. It's been great.
For anyone listening at home, if you'd like any more Earth and planetary science content, the links to all our social media are on the screen now or in the episode description. Thank you everyone for listening. Thank you again, Helena, and we will see you next week. Goodbye.